what I wanted to talk about, when we can discuss it, is how the while algebra can be quantized without any quantum field theory. So you can get the full quantum theory of local algebras without any information on quantum fields, Lagrangians, and all that stuff. You don't need it. And this is a major advance, in my opinion, in formulation of quantum field theory. And this particular paper I am reviewing is coming from Brunetti, Guido, and Longo. Okay? So I want to review now what it is that they are doing in succinct terms. Okay? So what is this
time already built in?
time? Yeah, Poincare group is there. So in the Poincare group thing, there is a time translation of, there's a four momentum, and the four momentum is future pointing. So it's assumed all through that the energy is a positive energy representation. So there is a future pointing four momentum, P mu, and that will define time. Okay? By exponentiating, you get a time evolution. So it is built into the Poincare group, but you may, up to Lorentz transformations, you can change the directional time by Lorentz transformation, which will change the fixed time slice that you're looking at. But that should not change any physics. Okay? So that is there. Okay? So I'm taking the starting point is the Poincare group, okay? The standard Poincare group, and it is acting on space-time. Once you have, give me the Poincare group, it acts on space-time, okay? Four vectors. It acts on that, maintaining the metric. Okay? So that is a given datum in the problem. Okay? And furthermore, from beginner's work, we know that this Poincare group has irreducible representations. And I will start by discussing how to quantize one irreducible representation of the Poincare group. Namely, say, take any one. Let's take a scalar field, and I'll show you how to quantize it.
How will interactions happen?
Interaction. The thing I am looking at is, in the case of the free field, the problem of how to incorporate interactions is, I would say, open. I will speculate on a possible way of putting the interactions, but I am not sure at all that it is correct. At the end, I will make a speculation. Yeah? But so when you start putting interactions, it seems that it is very difficult to avoid having to have quantum fields. Okay? It seems. Okay? And I will try to explain what the reasons are towards the end. Okay? As I keep going, I'll try to explain what the problem is which you confront when you go into quantum field, into interacting quantum field theories. Okay?
How will answer this earlier? We had some idea of thinking quantization earlier. Three things. There was some understanding. There are infinities, etc. problematic. But the problems for us always come from interactions. So is there a step towards them?
You may say that okay.
That's my concern. We want to go beyond this three things.
There is something much deeper, in my opinion, and that is the issue of how at all space-time emerges from quantum physics. You do not, for example, in quantum mechanics, you are just given the Hilbert space. I mean, experimentally, we measure only operators. We don't measure space-time. We just measure operator algebras. That is what we do. When we write Poisson brackets, it's for functions. Okay? Some functions on the phase space. Okay? So there is a deeper question, in my opinion, on how to recover space-time structure purely from observations already in quantum mechanics. How do I know when I am doing free particles, then I am working with R3? How do I know? I am just measuring operators on or classically mechanically functions on a phase space, and quantum mechanically I am measuring operators on Hilbert space. How do I know it is three-dimensional space-time? I don't know, okay, a priori. And then there is this all this activity of Gelfand about the spectrum of a commutative algebra, which seems to give a hint on to how to recover space-time from experiments. Okay? So, from the actual experiments we do, okay, whatever we may pretend, we don't see Lagranges. Absolutely, they are the things we make up. What we measure are observables and states. How do I recover space-time? Here, and then that's the activity of Alain Cohn, non-commutative algebra. All of these are aimed at resolving this issue, okay? Which I think is a very deep maths and physics problem. Okay? It may not have any relevance to calculations in LHC, okay? But it has a relevance to our conceptual understanding of nature. Okay? That's my opinion. The corresponding problem here is what emerges in interacting quantum field theory, or let us say, at the level of a theory which incorporates causality, is a net of algebras. Okay? So, can I do a similar reconstruction of space-time from this net? Okay? It's actually a net. Okay? So, I'll tell you what a net is. Okay? So, it is much more complicated. What emerges from causality. Causality compels you not to deal with just phase-space function, but something much more complicated. And how do I recover space-time from it? We don't know. Okay. So I would say that what these people are attempting is the first step in that direction. Okay. You may say that has nothing to do with, I don't know, phi 0 going to 2 gamma. Very likely. You may do phi 0 to 2 gamma without knowing this. Okay. But one would also like to know what it is, from where we get all this knowledge. Okay. So this is a step in that direction, it seems to me. Okay. And it is also very beautiful. Okay. So aesthetically, it is very pleasing. So what I have done is mathematically and conceptually very pleasing. Okay. So I would like to discuss that. How Wigner connects up to what we do. Okay. Wigner's representation theory of particles, how does it connect up to the kind of calculations we do? This is in that direction. So this is a clarification in that direction. So that's what I think the significance of this kind of work can be. So I don't think we know quantum field theory personally. Well, we know how to do calculations, but we are not engineers. We need to know what we are doing to an extent which is personally satisfying. That we don't know. Okay? In my opinion. So these are all attempts to clarify this issue. I don't know whether I have answered adequately.
You have not answered.
Hmm?
You have not answered. It's a point.
I am not saying anything about interacting quantum field theory at this moment.
So, previously you do have an idea.
No, I don't think so. We cannot write Lagranges. They don't exist.
No, don't use the Lagrange. What do you mean?
The operators that are coming there are operators which are unbounded. So we don't know how to multiply them. We can't multiply them. You will get infinite immediately. Okay. So what do we do? So we don't have to formulate, but there are issues. So if you want, and how is causality incorporated? So if you go like that for a free things, you will go in the Weidmann direction. That also, there's an alternate, I should say, there's an alternative approach to this issue, the Weidmann formulation. That also can be formulated, which answers causality issues also for free fields. Here, we want to avoid Weidmann fields, which are unbounded operators, by replacing them by bounded operators. And when you do that, you end up with this phenomenon algebras. So I would say that is the direction, but it also has consequences. For example, this analysis shows very clearly that if you try quantizing this, let us say Rindler wedge, take a free field, take is dynamics on a Rindler wedge. How do I do that? How do I look at quantum observations in the Rindler wedge? You need this kind of formulation. The creation annihilation operators won't work because they involve space-time integration all over. To even extract creation annihilation operators, you have to integrate over R3, whereas a Rindler wedge doesn't allow that. So what do you do? Okay? Which is a fact that Rindler wedge If you take the vacuum and look at observations in the renal wedge, you get thermal states. How does that happen? Where is the thermal state coming in the renal wedge? There is nothing, no temperature. It is just there. This calculation will show that this happens not only there, but it will also happen in the causal diamond and in every causally complete region. All of them are thermal states. There are no pure states which can come in local algebras. So then what is the integral entropy? They are all infinite. You just take trace. There is no state for these algebras. There is no density matrix intrinsically defined. So you can take density matrices from outside, then they are all impure. There is no pure state. So what does it want to do? So how do I compute entanglement entropy, for example? Or how do I look at entanglement of two space-time regions? Unfortunately, the Weidmann framework doesn't give a hint. And certainly Lagrangian mechanics doesn't give a hint. So this may be towards clarification of this issue. But by the way, I am not defending, I am not a spokesman for these methods. I find them very beautiful. But if they are wrong, which will imply quantum field theory is wrong, I would not be disturbed.
No, they are not even wrong.
Which one?
So, point is they have not achieved anything to say whether it is right or wrong.
That's not correct.
That's not my conclusion.
That's not correct. They have proved spin and statistics theorem. They have proved Bayes statistics. They have proved the CFT. What is it? This duality of what is it? This Schwinger. What is it? Kuber, Martin Schwinger came state, and this boundary at the top thing, giving the cross channels conformal field theory. They have proved. So there is a class of results which are not which have been actually proved. Now, you may say they are very limited. I would agree. I would not dispute that.
We do have some idea of spin statistics theorem.
We have many ideas of many things.
No, I don't. There are several things here which is not even answered.
Okay.
Which was answered earlier and experimentally. Finally, for me, experiments.
Yes.
Tell me what is the thing that I can predict.
Again, I repeat that, for example, spin and statistics theorem was not answered at all in quantum field theory, except in the Lagrangian things, some mechanics, some manipulations. They were not answered. It was answered much later in the Weidmann framework by Dell'Antonio. Here it is answered by totally different technology. Bayes statistics was not derived in quantum theory at any level of rigor at all, long ago. You can do manipulations with Lagrangian, but these people will claim that I think is correct. The Lagrangians don't exist. So, in a real way, they are all infinite. They're classical objects, they are infinite.
Free theory, existence of Lagrangian is unimportant. It's only particles who came. They go with uniform velocity like Newton's laws. Effectively, Newton's laws. Newton's laws.
I do understand. You are just get differential equations.
Not differential equations. They will just move without any change in the velocity.
There is no particle. No. Quantum field theory, there is no necessary particles. How do you know there are particles?
But we have particles.
That's not the experimental issue. I am not challenging experiments. I am challenging how.
But in what way can be connected to physics?
Which one? I am telling spin and statistics is.
The spin and statistics of what?
For let's say Wigner representations, under which 2 pi rotation is +1, they show that cause.
Are they for particles or for some fields which exist all over the universe?
No. Take observables, which are localized in some space-time region, and take
the observable. I have particles which are observable.
No.
Maybe localized to some extent.
Here, the statement, you may not accept this, but I am not, I again repeat, I am not pushing this. Even in the Wigner thing, what they are
I'm confused about what is achieved out of all these exercises. I find nothing. Except what we know already in some new language in the big course.
It is, it's up to you. Again, let me say that I am not a politician trying to push this in. I am telling that this is not a reformulation of what's already, it's not a repeat of what is already known. That is simply not correct. Uh, they derive the things we know should. If it starts violating Pauli principle, there is a problem. But the derivation of the Pauli spin statistics theorem from a local observations is a different order of magnitude problem. And these people have solved it. It's not at all trivial. It can also be solved using Meitner framework, which was solved again with a lot of difficulty by Delantonio. And before that by Zumino and Lutez and Zumino and others. It was not trivial.
They're all relativistic. They're all relativistic.
The proof is only in the relativistic context.
But you do have non-relativistic only.
You cannot be proved. It cannot be proved. As I said last time, nothing goes wrong if you replace spin integral particles in non-relativistic physics with stated determinants. Nothing goes wrong. Physically, experimentally goes wrong. But in terms of calculations, spectrum of the Hamiltonian, nothing goes wrong. This is a fact. Okay? So, how intrinsically in non-relativistic physics, there is no rule which says you can't do that, you should do that. There is no such thing.
No. For example, if I take Dirac equation, okay? Now the Dirac equation in a non-relativistic limit will automatically involve antiparticle.
But you are starting from a relativistic thing or if you write Pauli equation for spin half, I am telling you, Pauli equation is not a relativistic spin half particle equation. And you quantize it, taking the wave functions with the slated, with the both symmetrized things, nothing will go wrong.
No, I don't take Pauli equation alone. I take two Pauli equations.
Take any n of these things.
Pauli equation, two Pauli equations will turn up a particle and antiparticle in the limit of Dirac equation goes to non-relativistic limit. When we say non-relativistic limit, there is a scale involved. Some V by C relations will be involved. So that will be there. Whatever difficulties which we have are applicable only up to the scale of particle antiparticle creation possibility. There is an energy scale which will be involved. So there is some limit. Of course, the point problem will happen at the level of up to what scale I can believe that scale. Now, at the fundamental level, I may be able to prove if I have a relativistic thing. I'm taking a non-relativistic limit, it will be always embedded in that. I don't find any problematic.
That's okay. I mean,
I don't find it anything wrong out of all these exercises.
Let me not challenge your acceptance. I am not agreeing with you, but it's okay. I don't know.
I am also not agreeing with you, but it's up to you.
Yeah.
Can
Sure.
I say that?
Okay. Okay. So let me go on. So what I want to show here is what is this? What is it that these people are doing? So what is involved are only two. I am going to quantize. I am going to give the Weil algebra, quantization of the Weil algebra, deriving the Fock space by a set of rules which will not appeal to quantum fields at all. It will only take the Wigner representations, and from the Wigner representations, they are all free particles. For free particle Wigner representations, it will end up by constructing the full Fock space. Full Fock space for the local algebras, and we will see as we go along, as I said earlier, because you are dealing with space-time, localized space-time regions, there is no way of constructing single particle excitations at all in this picture. Okay? Because you cannot, single particle excitations require creation annihilation operators, and they cannot be projected by integrating the field over a finite space-time region. That is not possible. You need d cubed x all over space. Okay? But we are dealing with local algebras, and therefore you cannot, but something else happens. We will get the Undru predictions, and we will get spin statistics, which I think I proved last time. And as we keep going, we will see that the thermostates with which we are familiar, the Kubo-Martin-Schwinger thermostates, naturally emerge from these calculations. And emergent from this picture are also all results which happen nowadays in, for example, in the papers on DCT space. In DCT space, you are immediately faced with the problem that there are horizons. There are cosmological horizons. So there is a problem. Okay? And the algebra that are coming are the type of algebra you will be dealing with. What do you do? Okay? And there have been a lot of struggle in trying to find out how to, what is it that we are doing there? What are the things we can observe there? And the last contribution in this direction was again by Longo, Witten, Chandrasekharan, and Pennington. There is a paper by 4 people, and you see that they are using technology from here. So there is a community which is involved in this. How it will evolve in later I cannot tell. This is something to be historically determined. But something is happening in the context of quantum theory, in my opinion. So what we start with Poincare group. The Poincare group we are going to deal with is a connected Poincare group, P plus. So with all determinant plus 1. Okay. So the P plus with determinant plus 1 contains all the things connected to identity, and it also involves CPT. Okay. What we call CPT, namely the total reflection. This is what we start from. Okay. So we start with the geometrical group, which I call P. Okay. And we assume, say, we can borrow from Wigner that I'm given a representation of this group by rho, which I have denoted by rho, okay, and I am also given the vacuum representation. It turns out that the vacuum representation seems to be very important. Okay? So in the vacuum representation, it maps rho maps all the elements of the Poincare group, the identity, when acting on the vacuum vector. Okay? So the vacuum representation is given by simply complex numbers times the vacuum. Okay? So because I have introduced CPT in this P, there is an operator which is anti-linear, which anti-unitary, which we call which reverse. So I know since the moment I'm given the Poincare group, I know it acts on space-time. Okay? And in particular, we know that there is an operator which we can call CPT, which reverses all the coordinates, okay? X1, X0, X1, X2, X3, and which we call normally CPT. Okay? The CPT under rho will necessarily be anti-unitary. The reason is, the reason why CPT becomes anti-unitary is because we want the energy to be non-bounded below. Okay? If Wigner showed long ago that if you have a time reversal or a CPT and you represent it by a unitary operator, the Hamiltonian will not be bounded below. Okay? And he, for that reason, said that CPT should be bounded, should be anti-linear, okay? Anti-unitary. So we have unitary operators, except all of which are connected to identity of the Poincare group, plus CPT operation, which is anti-linear, anti-unitary. There is no independent operators called CP and T. I call them CPT. Actually, I call them theta later in theory. So we don't say C and P and T exist separately. Yeah. So this is what I am starting from. Yeah. Then what I do is
said that reason for anti-unitary energies bounded.
Sorry.
Energies bounded below. When you not have any field, that is the definition of energy.
You know, okay. So better way of saying it is that the spectrum of P mu should be in the forward light code. Okay. The spectrum of P mu as an operator in the representation should be in the forward light code. Okay. That is well defined. Okay. Purely from representation theory, that's well defined. And what we call CPT or theta should not take it into the backward line. That is the intrinsic way of saying it, which incidentally implies that the Hamiltonian is bounded. Whatever be the choice of the Hamiltonian is bounded below.
So the starting point is Poincare group.
Algebra
of operators which are in the Poincare.
Yes.
Which are the Lie algebra of the Poincare.
Not the Lie algebra, preferably finite transformations, but also Lie algebra. I will use them interchangeably because the Poincare group has a well-defined Lie algebra.
So that is the starting point.
Yes.
And you cannot ignore DC now.
No,
For visitor, you should go to another algebra.
no, no, that's not what happened. In the case of the de-Sitter space, uh, de-Sitter space, the group is SO15. Okay. So the calculation is not done by these techniques. The calculation is done by first noticing that for other general reasons, the algebra outside the horizon, there is a horizon, observer dependent horizon, and what is available for the observer from other very general arguments, which I hope I will come, is what they call type 3-1, which is in some way most complicated algebra you can imagine, and in particular, it does not have anything, any operator with finite rays. There is nothing. There is nothing you can find with finite rays, so you cannot write density matrix there. So, what do I mean by observation? You don't know. Yes. Meanwhile, there is a paper by Hawking and Gibbons long ago, where they speculated that even for de-Sitter, the Bekenstein-Hawking formula applies for entropy. Namely, is given by the area of the horizon. That is pure speculation. Can I derive it?
It's a semi-class.
Ah.
No, I have also done that.
Okay.
3 dimensional. Good. 3 dimensional.
Okay. Can I derive it from quantum field theory? So this is the attempt of these four people here. You cannot derive it from the nature of the algebra. It's of type 3-1. As I told you, there's no intrinsic density matrix. So they are dealing with this and enlarging this operation of algebra in particular means, basically including also the algebra in the beyond the cosmic horizon in a particular way, and eventually converging it to another algebra they call type 2-1, which does allow a density matrix. Whether we accept their calculations or not, I'm not sure. I don't even know that they are thinking they have proved it. They're making a suggestion. They say it's a move in this direction. Why type 2-1? Type 2-1 happens to have a density matrix with a maximum entropy. It's a peculiar thing that in type 2-1 algebra, all density projection operators have finite rays, and furthermore, there is one with a maximum trace. So maximum entropy. So they calculate it and they find this given Hawking's formula up to an universal additive constant. That is, you take the difference of, it's just renormalization. They call it the renormalization constant. It's an overall additive constant that depends on the details of the model. So, to arrive at that thing requires a lot of effort. It's not simple at all. And it is not perturbative. There is no perturbation, and they don't use free fields, or they don't use representation theory of this kind. They use representation theory of the fundamental algebras. So, if you ask, are they right or wrong? I don't know. But it is certainly a very impressive.
This is also a fundamental.
All these are going to, this one eventually will be a fundamental algebra.
But what type?
This will be type 3-1.
There will be problems there also.
If you try to find a density matrix, yes. Every local algebra in Poincare group is type 3-1. There is nothing is not a type 3-1. Okay? And that comes from local algebra. That comes from, I would say, apparently very good physical principles, namely finiteness of the density matrix. Then finite numbers of the number of excitations, which is defined mathematically in local. So there is some rule, something which counts how many excitations you can have in some range. I'm not familiar. I know that paper, but I'm not read it carefully. And requiring that it is finite requires that this algebra of type 3-1. So there is an argument in this direction. And in particular cases, they have been checked. So free fields, they have been checked. But free fundamental algebras, they have been checked mathematically. So there is some supporting evidence. Are they absolutely carved in stone? I don't think so. These things are evolving with teachings. I don't know. Certainly, if you put gravity, I don't know what. I don't think anybody knows.
Already you have been talking about curved spacecraft.
Hmm?
Already you are talking about curved spacecraft, which is in considered as a gravity. Like de-sitter or
Ah.
even Rindler.
Rindler is not curved.
Well, it is not curved, but it has horizon.
It has horizon. Okay. The horizon is not excluded here.
No, Rindler is essentially same as uniformly accelerated.
Union accepted. Uniformity.
Yeah, uniformly accelerated. Uniformly accelerated by deep equivalence principle, I'll say it's on that I can have that. I can say that there is some gravity which is constant in principle.
Yeah, but it is not. I don't think that you can say that, but the analysis which is done is more appropriate for only concrete group structure is used in this calculation.
Right.
Nothing more. This classical arguments about accelerated particles is not used here. It is. Can I use it? Well, if it helps you to prove something, fine. I have no problem. But it is not used. It is not a tool that is entering this. But as I say, I have no objection. Somebody uses it. And then finally comes back to some quantum field theory arguments. Quantum theory arguments. Let me tell another very related problem. Because, and this is I think again a deep problem, which is not called very well. This is that the bigger representation, there is a representation which has zero mass and the spin components are infinite dimensional. So instead of having finitely many spin components, because infinitely many spin components. That object, that thing there, at this moment, from what I understand, it is the proper treatment. For example, even the level of this picture has not been done. And certainly, if you try writing local quantum field, just write a local quantum field fulfilling causality, you cannot do it. There are proofs that cannot be done. There are what they call cone, localized fields in cones due to Bohrs and others.
But will it have bounded energy operator?
Yes. Energy is finite. Energy is finite. See, energy is zero. The P mu is zero. It's a light-like particle. Except that at each point of the light-like cone, you have infinite number of spin components which can be excited. So there's nothing wrong physically. This has been noted by many people. Could be the thing that creates dark matter. There have been proposals like that, but we don't know.
Matter is far from all these things.
I don't know that because that object there you're writing, is very difficult to make it interact with normal matter. It does interact with gravity. So there have been.
You don't know what is gravity here.
No. If you write G mu, you can write energy movement finger for gravity, and there have been semi-classical arguments, especially by Bert Schroer, where he tries to couple G mu to these fields. And it will not, if you try writing such G mu, where this object is involved, which is now locally on a code, which other field you would not succeed. He says, but we can write down an energy movement principle, and that is G mu coming from the background here. So he is speculating that this could be a component of dark matter, but he did not pursue the matter. So there is this little thing going around, which is probably worth looking, but I have not looked at it carefully.
Not a lot of speculation going on.
Yes.
Even there is no need for dark matter is also people do talk. There is no need for dark matter also something people do talk. That will be far-fetched to attempt right from here, from the fundamental formulation, where you have to achieve what is already known to some extent in much better light than what I bothered.
So but sure may be wrong. I don't have anything to say. But there is this work Bacon. So, but definitely the attempt at formulating, treating dark matter, not this infinite component, infinite number of states.
Massless infinite components representation
is very much open.
That's what you're saying.
It exists. There's nothing wrong physically.
Which exists, I don't know, but it's a possibility to exist.
It exists in the beginner table. I don't know, but it exists in nature. If it does not exist in nature, we would like to understand why it does not exist in nature. Nothing prevents it. But it may be related to why high spin particles don't exist. Master, it could be related. We don't know. So,
Pauli Luban's inventor. Pauli Luban's inventor.
So if you write Pauli Lubanski vector, it will have a spectrum. Infinite number of components. The sigma that comes in the Pauli Lubanski will be infinite dimensional matrix. Okay. I don't know whether anybody has written in that language, but it can be done. Okay.
Theory, representation theory allows any mass and any space. Not all of them are in nature.
So we would like to know why.
I agree. But we have only some small set of them as available to us in nature. That is good. Spin 1, spin 0, spin half. That's all maximum. The rest of them are composites.
Okay. We don't know what is a composite. Let me also
composite is essentially, I will say that they exist as some collection of objects.
We don't know that. We can't separate them. What I mean is,
they need not be described as a fundamental object.
We don't know. For example, yesterday.
No, we don't know several things. But I'm saying that these are the only things available to us. Even there, we don't know. Even proton, I don't know. Neutron are also composites.
Are they composites? The Skrimian formulation. Neutron is not a composite. It's a solid organism.
They are all quarks.
We don't know that. That's another interpret. So we have here the same object described two different ways. Can I say one is that? Should I be a partisan? I'm not a partisan. Okay? I don't know. I think this concept is vague. There are nuclei with very high spins. Presumably they have electricity description. What are they? Have they done it? Last Friday, Rajiv gave a talk on how to describe a electricity wave equation for Skriniar.
Again, there are only three things. He doesn't have interaction. He doesn't have interactions.
He tries. I mean, poor man is trying.
No.
So,
even if assume that they have some electromagnetic interaction, the whole thing theory may violate causality.
okay.
In fact, that's one of the problems which he faces. If you want to, I asked him what is the coupling to electromagnetic.
The main problem I see is that it's not unitary. But anyway, it's a good attempt at how to make quark this script model. I think it's a good attempt. Let us say it's open. These are issues to be clarified. So there are many issues at a foundation level, which certainly many of you would like to understand. So it's getting late.
Sorry, I started asking too many questions.
You can ask, no problem.
That's
It's getting late in the sense that there is no problem. Okay, I have no problem. When I say late, there is a colloquium downstairs at 3 o'clock. Okay?
Yeah.
I don't know how many people want to go there. I don't know what it is about. So for such issues, I can stay here and go and talk with you.
So the tachyon will not be covered by, even
No.
though it is a representation.
Yes, no. If you the moment you put in negative particles spectrum, not in the forward light code, PIMI is not the entire physics as we know it goes fat. Causality goes fat. The system gets unstable. Of all things, Wigner's is something else. I say, what is it? The showing our proof. that the ATM mass is positive goes fat. Okay? Because that uses basically the properties of the Poincare group. Okay? Or which is everything will go fat. Okay? You may say, okay, goes fat, so what? So maybe the world is unstable. I don't know. So we don't allow tacklers.
It is probably describing an unstable situation where only a composite scan probably can be seen. It will have positive, might have positive. Each individual may have that kind of thing. Composite may have finite positive.
I have nothing to say. I have kept away from that. There are papers certainly by George and also G. Ramachandran, who was the colleague of the boss of Parsari here. He has written, I think, at least discussed with me. I don't have anything to say. If they are found will I be shocked, I will be highly surprised. Okay? But okay, we say, okay. We carry on with something else. Try to see how to.
They are not human space or for example, God, when we try to do tachyon quantum, that is scalar, only scalar. Arends and Sudarshan, they were using indefinite metric space. So that is the kind of. So the operators acting on some indefinite metric space, can you make it reasonable or not?
I don't know that.
I forgot all of it. Just look at what happened.
So, let me just say the beginning part of it, and then we will meet again next time. Okay? So, what we do is the Poincare group algebra, Lorentz group algebra, we know, for example, from the Cartan-Killing form, which is intrinsic to the algebra, that there are certain operators which we call Bose. Okay? The Lie algebra can be written in some basis, and there are three operators generally independent in the Lie algebra, which we call K1, K2, K3. We call how we label it is up to us, and there are compact generators which are called let's say J1, J2, J3. Okay? The split is not unique. Okay? You can make some other. You can make a Lorentz transformation. The split will change. Doesn't matter. Pick one. Pick one of them and call it K1. Okay? So this is certainly the Lie algebra of P plus. Okay? So it's a finite dimensional matrix. If you take a finite dimensional SL2C representation, it's a finite dimensional matrix. Okay? Then in this representation, since the Lorentz group is acting on space-time, okay, so and we can imagine, we can look at the orbit of K1, the boost one, it will give you some direction in space-time, in spatial direction, and I can look at the orthogonal directions, call it just label it 2 and 3, okay, randomly, and look at pi rotation around the first axis. Is pi rotation uniquely defined? Yes, around first axis. So the pi rotation around the first axis will not change the first axis, which you chose, or it will not change K1, but it will reverse the sign of the two orthogonal directions corresponding to 2 and 3 in space-time. Call it G pi. This is uniquely defined in the group. Okay. G pi squared is 1 okay, for boson. Okay. Now, so what do we do next? Now, if you give me this K1 and give me this pi rotation, already with K1, the Poincare group is acting on space-time. That is given to me. And no fees, but it's acting. So that picks out a Riddler wedge. Namely, the Riddler wedge where it is, it creates orbits without leaving the wedge. Actually, it gives two Riddler wedges. One on the right half and the other in the left half in the 1-2 plane, 0-1 plane. So we had two Riddler wedges, which I call W and W prime. Okay? So I have got it now, until now, purely geometrically from the properties of the Poincare group. and this action on space-time. Okay. Then what you do is take this g pi, which I have got from the choice of the k1 at the beginning, multiplied by theta. Theta is a CPT operation which reverses all the coordinates on space. These are all acting on space-time, and I'll call it J for the wedge W. So what does g pi do? It acting on x0, x1, x2, x3, it reverses the sign of 2 and 3. Theta reverses the sign of all of them. So the product does not reverse the sign of 2 and 3, but it reverses 0, 1 to minus 0, minus 1. Okay? So it takes you from the right real wedge to the left real wedge. So given K1, I have two real wedges, which I'll call W and W prime. W prime is obtained by W by acting with JW. This small JW is just a geometrical operation. No claim of what is it, anti-unitarity or anything like that. It's just geometrical operation. And now the main point is that this JW commutes with the boost time evolution coming from the boost operator, which is called exponential ITK1. This is in the Lie algebra of finite dimensional matrices, and this operator commutes with this object. Until now, no big deal. Now I will go into quantum theory. I have a representation rho of these operators. So I take rho of JW, small jw, and I call it capital JW. But since small jw involves the CPT operation, theta, capital JW is anti-unitary. This is very important. Only in the representation space is this JW anti-unitary. And I will also call the operator representing exponential ITK1 as exponential IT with a capital K. Okay. Now, what is the important things? Here, the square of capital JW is 1. Because it reflects twice, it is 1. Okay. And like I showed, well, geometrically, capital JW must commute with time evolution of K1, because the whole idea of Wigner is that the geometrical operation are maintained in the unitary representation of the group. Okay? So capital JW commutes with exponential IT K1. Okay? But there is an I there. So this shows that capital JW, when it acts on exponential minus pi K1, it reverses the sign. It makes it plus I pi K1. This is an important equation. I will show later that this exponential IT K1 can be analytically continued in T up to I pi without any problem. I will show it explicitly. And this is what gives you this analyticity in a strip. Okay. So I can go up to in T plane, I go up in the imaginary direction up to this boundary pi. And at that point, JW, this operator, which is squaring to 1, reverses this exponential pi minus pi K1. Okay. So what is the consequence? Okay. If I call the standard notation of exponential minus pi K1, it is delta to the power of half W. W is because it is associated to a wedge. Okay. So I take delta to the power of half W of this operator and construct this operator SW. Okay. I can do it by hand. Okay. What is this SW? This will be our modular operator, okay, which will tell me how to deal with the Hilbert space. And for square SW, because of this reversal of sign, when I square it, this term will cancel out. JW squared is 1, so we will get identity.
And delta for half is 5 K.
Yes.
That's a definition of delta.
Yes. Okay. So when I pull it through, it reverses sign. So in the square, it cancels out. Okay. So you find that SW square is identity and then JW square. So it is SW is an involution. It is not, JW is unitary. It's coming from CPT but the SW is not unitary. To take SW star SW, you will get some. To take SW star SW, where is SW? Here. The J's will cancel out, and you will get delta to the power of half. Okay? Which is squared of delta to the power of, which is delta. So you will get simply plus pi k1, exponential of pi k1. That is an unbounded operator because this k1 eigenvalues are from minus infinity to plus infinity. So SW squared by no means is a bounded operator. Okay. It also shows what some people do to think of this k as a what's it called? They call it modular Hamiltonian. Use this as a Hamiltonian. It's also wrong because if you do that, this k1 is not bounded below or above. It is not a Hamiltonian. It's not a true Hamiltonian at all. But the language is growing in the literature that it is something they call the modular Hamiltonian for whatever the reason.
So time evolution operator.
Hmm?
So time evolution operator.
Some t is not time here. In some parameter tau, I should have called it tau. Some parameter for the one parameter group I'm dealing with. That's all. So this SW is a modular operator, and JW is called the modular conjugation. Okay, so I will try to go quickly. All these operators are defined on a Hilbert space or the one particle space. Okay. So I started the Hilbert space from beginner. It has a vacuum representation, which I call H0. So that is C times the vacuum state, which they have called E0, plus there is some plus one particle space. Okay. That is given to you. Okay. Beginner gives it to you. Can be any spin. Okay. Any mass, any spin, massless, it doesn't matter. I don't know what happens with this infinite component object, but the remaining thing is nothing happens. Now I see what happens if so all these operators are well defined, but notice that there is another modular operator which I will obtain by conjugating with the JW. Notice that small JW takes a right little wedge to the left little wedge. So if I take this operator and I conjugate it with JW, I'll get another modular operator, which is delta to the power of half acting on the right left times JW. Okay. And conjugate it, okay, or I put a half here, but it's better to conjugate the original one, which is J times plus half, okay, and conjugate it. So it takes the right wedge to the left wedge. Then you get under this delta to the power of half on the left times J. Whereas previously I had it on the right. So I got two modular operators, one for the left wedge and one for the right wedge. Okay. So, namely S. What do I do with this S? It's unbounded and not an easy operator to deal with. So what do I do? Okay. This S is defined to pick a real subspace of your Hilbert, one particle Hilbert space. Remember that for quantum field, I smeared with real functions. This is the analog of that choice of real functions in quantum field to get a symmetrized Fock space. And here I get it by using this S. And this is, I think, a miracle by saying that the real subspace of the Hilbert space consists of all H in the vectors H in the Hilbert space, which are invariant under this S, this modular operator. So, anything S squared is 1. So, H is real means it is of the form 1/2 of the identity plus S. H. Okay. So, if I apply S here, S squared is 1. So, it is unchanged. So, this is like a projection operator. Okay. This is a real subspace or the full Hilbert space. But notice that this real subspace depends on W or S. It changes from patch to patch. Okay. From W to W prime, you get different real subspaces. This is important. Okay. Now I can define the Weil algebra. Okay. H is So I take an element of the real subspace, which is given to me now, and I take an element of W y for the left edge with elements of this real subspace, say two of them, H1 and H2, and I'll give you the product. Okay. What is the product? It will be W of y of W H1 plus H2 times a phase, which is this one. And how do I get this? I see what I get for free fields. It's where here I had the imaginary part of the two test functions, and I just replace it by the scalar product, the two real functions, two elements, real subspace elements, put an imaginary part and some factor that you get, which you can get from the free field calculation. Okay. So this is what defines for you the Weyl algebra, along with the reality condition that W of X, Y W H star is W minus H. Okay. So the main point, so next time I'll see how I'll show you how to get the full Fock space for W. But the main thing here is that until now, I have not used any field theory whatsoever. I will simply use Poincare group and its properties, the fact that it is acting on space-time to get hold of CPT and what is meant by K1, at least to enable my thinking. And I got the Weyl algebra, and I have got a representation on the one coming from the Hilbert space of one particle wave function. Okay. And I've told you how the algebraic structure has been given. But I am writing H in the exponential. W, these H's are coming in the exponential. If you write this F is carrying for a free field. So, for in terms of field, it is exponential I phi F. Right? So F is getting replaced by H. So things are coming in the numerator. So if I try to expand it in powers of H, I'll get all powers of H. Okay. So what do? What is the meaning of two H's? Both are elements of the Hilbert space. Okay. We will see that this can be also resolved, and it will generate the full symmetrized Fock space. Okay. And I'll get the full representation for the Weyl algebra for the Miller wedge. Okay. And also for the complementary wedge in such a way that causality is maintained. So I will do that next time because it is fairly late. Make a quick review maybe next time, and I'll keep going. Okay.